The Heisenberg Uncertainty Principle is often introduced as a limit. We cannot know certain pairs of properties, such as position and momentum, with perfect precision at the same time. But this principle is more than a warning about what we cannot know. It also explains why electrons behave like waves, why tunneling can occur, and why measurement at the quantum scale is never completely passive. In this video, we will look at 8 important applications where the uncertainty principle helps us understand real technologies and real scientific frontiers. The uncertainty principle is not only a limit. It is also a doorway into modern quantum technology. Ordinary light microscopes are limited by the wavelength of visible light. If the object is much smaller than that wavelength, the image becomes blurred. To see much smaller structures, scientists use electrons instead of visible light. The uncertainty principle reminds us that particles such as electrons cannot be understood only as tiny balls. They also have wave-like behavior. This wave nature allows electrons to reveal details far smaller than those visible under ordinary light. To locate very small structures, electrons must have very short wavelengths. This usually means higher momentum and higher energy. But a high-energy electron beam can disturb the sample. It may heat the sample, knock atoms out of place, break delicate bonds, or damage soft biological material. So electron microscopy is always a balance between sharper resolution and protecting the object being studied. Electron microscopes help scientists study cells, viruses, crystals, metals, and nanomaterials. The uncertainty principle does not simply block measurement. It teaches us how position, momentum, wavelength, and resolution are connected. Electron microscopes show how quantum limits can become powerful tools for seeing the very small. A scanning tunneling microscope uses an extremely sharp conducting tip placed very close to a surface. The tip does not need to touch the surface directly. Instead, it detects a tiny electric current produced by quantum tunneling. The uncertainty principle helps explain why electrons are not trapped like classical particles with perfectly sharp boundaries. Their quantum wave functions can extend slightly beyond a surface. Because of this, an electron has a small chance of tunneling across a narrow gap. The tunneling current changes strongly with distance. Even a tiny change in height can produce a measurable change in current. By scanning the tip across the surface, scientists can build an image of atoms one point at a time. Scanning tunneling microscopy shows how a deep quantum principle becomes practical technology. The uncertainty principle helps make atomic-scale surface imaging possible. What seems strange in theory becomes a tool for seeing the arrangement of matter itself. Quantum tunneling turns uncertainty into a way of mapping atoms. In ordinary circuits, electrons are often treated as moving charges. But inside very small semiconductor devices, electrons are confined to tiny regions. At this scale, the uncertainty principle becomes important because confinement affects momentum and energy. When an electron is restricted to a very small space, it cannot have just any energy. Its allowed energies become separated into quantum levels. This is one reason nanoscale materials can behave very differently from larger pieces of the same substance. In some devices, tunneling is useful and carefully designed. In others, unwanted tunneling can cause leakage current and reduce performance. The uncertainty principle helps engineers understand why electrons may cross barriers that would seem impossible in classical physics. Modern electronics, lasers, sensors, and quantum dots all depend on controlling electrons at small scales. The uncertainty principle is not just a classroom idea. It is part of the design language of nanotechnology. At the nanoscale, uncertainty becomes part of engineering design. Quantum cryptography uses quantum systems, such as photons, to help protect information. These systems can carry secret keys between two users. The security comes partly from the fact that quantum states cannot be observed freely without consequences. The uncertainty principle is closely related to the idea that certain properties cannot all be known exactly at the same time. When someone measures a quantum system in the wrong way, the act of measurement can disturb it. This disturbance can reveal that eavesdropping has occurred. In classical communication, a hidden listener may copy information without changing it. In quantum communication, measurement can leave detectable traces. This gives quantum cryptography a special kind of security based on physics, not only on mathematical difficulty. Quantum cryptography shows that uncertainty can be useful. What first appears to be a limit becomes a protection. Nature itself helps warn us when a secret quantum message has been disturbed. In quantum cryptography, uncertainty becomes a guard against hidden listening. A classical computer stores information in bits, usually represented as 0 or 1. A quantum computer uses quantum bits, or qubits. A qubit can exist in a quantum state that cannot be described as simply 0 or 1 before measurement. The uncertainty principle helps us understand why quantum information is different from ordinary information. Some properties cannot be fixed with perfect certainty at the same time. This makes quantum states powerful, but also delicate. In quantum computing, measurement is not a passive act. When a qubit is measured, the quantum state is forced into a definite result. This is why quantum algorithms must be carefully designed so that the final measurement gives useful information. Quantum computing gains power from superposition, interference, and entanglement. But these same quantum features are easily disturbed by noise and measurement. The uncertainty principle helps students see why quantum computing is both promising and technically difficult. Quantum computing is powerful because it works with uncertainty, not around it. Metrology is the science of measurement. At very high precision, measurement is no longer limited only by poor instruments. It is also limited by the quantum behavior of nature itself. The uncertainty principle tells us that improving precision in one quantity can increase uncertainty in another. Instead of ignoring this, scientists use it as a guide. They design experiments that place uncertainty where it matters least. Quantum sensors can measure extremely small changes in magnetic fields, gravity, acceleration, rotation, and time. These tools may help in navigation, medicine, geology, and fundamental physics. Their power comes from controlling quantum states with great care. Some advanced sensors use techniques that reduce uncertainty in one chosen measurement direction. This is often called squeezing. The total quantum uncertainty remains, but it is redistributed in a useful way. Quantum sensing shows that uncertainty is not merely an obstacle. It is a design rule. By understanding the limit, scientists can build instruments that approach the edge of what nature allows. Quantum sensors turn uncertainty into a guide for measuring the almost unmeasurable. Atomic clocks use the regular behavior of atoms to measure time. Instead of relying on a swinging pendulum or a quartz crystal, they rely on precise quantum transitions between energy states. These transitions provide an extremely stable reference. The uncertainty principle has a time-energy form. It tells us that there is a deep relationship between the precision of energy and the time over which a quantum state is observed. This relationship matters when scientists measure very sharp atomic frequencies. The more precisely we define a transition frequency, the more accurately we can measure time. Atomic clocks use carefully controlled atoms to reduce unwanted disturbances. This allows them to become far more accurate than ordinary clocks. Atomic clocks are important in GPS, telecommunications, navigation, and scientific research. They also help test deep ideas about gravity and relativity. The uncertainty principle helps explain why precision timekeeping belongs to the quantum world. Atomic clocks show how the smallest quantum changes can guide the largest human systems. From satellites to global networks, modern timing depends on the behavior of atoms. Atomic clocks show how quantum precision keeps the modern world in sync. Living systems may look classical at the scale of organs and organisms. But inside cells, many processes happen at the scale of molecules, atoms, electrons, and protons. At this scale, quantum behavior can become relevant. Some biological reactions may involve particles tunneling through energy barriers rather than simply going over them. This can matter in enzyme reactions and molecular transformations. The uncertainty principle helps explain why particles are not always confined to one exact classical path. In photosynthesis, energy moves through molecular structures with remarkable efficiency. Researchers study whether quantum effects help guide this transfer. The full story is complex, but it shows how quantum physics can enter biological questions. Some animals appear to sense Earth's magnetic field. One possible explanation involves quantum processes in special molecules affected by magnetic fields. This remains an active area of research, but it shows how quantum ideas may help explain biological navigation. Quantum biology does not mean that life violates physics. It means that living systems may sometimes use the physics of very small things. The uncertainty principle helps us avoid forcing classical certainty onto processes that happen at molecular scale. Quantum biology reminds us that life is built from particles that do not always follow classical rules. The Heisenberg Uncertainty Principle tells us that nature does not always allow perfect certainty. At the quantum scale, some properties cannot be pinned down together with unlimited precision. Yet this limit is also a source of insight. It helps explain electron waves, tunneling, quantum measurement, nanoscale design, precision sensing, and the behavior of matter at very small scales. That is why the uncertainty principle appears in electron microscopes, scanning tunneling microscopes, semiconductors, cryptography, quantum computing, atomic clocks, quantum sensors, and even emerging studies in biology. For students, the key lesson is simple. Uncertainty is not only a barrier to knowledge. In modern science and technology, it is also a doorway to discovery. Uncertainty is not only what limits us. It is also what teaches us how the quantum world works.